Welcome to The Explainer, where we break down big ideas by going straight to the source material. Today, we are getting into some really fundamental stuff, the rules that literally dictate why anything happens in our universe. We're talking about the second and third laws of thermodynamics. All right, let's get right into it.
You know, it all starts with something you've seen a million times. You pour a hot cup of coffee, and it cools down. Of course it does. But have you ever seen a glass of iced tea just start boiling by itself? No way. And that's not a coincidence. It's actually a clue that points to one of the most profound laws in all of nature.
So here's how we're going to tackle this. First, we'll look at this whole idea of spontaneity and why we need a way to predict it. Then, we'll unpack the two huge laws that give us the answer. After that, we'll see them in action with some real-world examples. And finally, we'll zoom out and look at the big picture.
Okay, so first up is what scientists call the spontaneity puzzle. What we're really looking for is some kind of universal property, a single number, that can tell us ahead of time, is this thing going to happen all by itself or not?
And here it is. The property we're looking for is called entropy. Now, you've probably heard it called disorder, and that's kind of right. But the absolute key, and this is the part people forget, is that to use it properly, you can't just look at the thing you're interested in, what we call the system. You have to account for everything else around it, the surroundings.
This whole idea of the system and the surroundings brings us directly to the first major rule we're talking about today. It's a law that basically paints a giant, cosmic one-way sign on every process in the universe. This is the second law of thermodynamics.
And there it is. That's the core idea right there. Any change that happens all on its own, no pushing, no prodding, just happens, must increase the total entropy or disorder of the entire universe. It's such a simple sentence, but it's incredibly powerful. It literally governs the direction of time.
So how do we actually calculate this? Well, it's surprisingly simple. The total change in the universe's entropy, that's what delta S univ means, is just the change in our system's entropy plus the change in the surroundings entropy. You just add them up, and that simple sum holds the key to predicting, well, everything.
Let's circle back to our hot and cold drinks. When heat flows from a hot thing to a cold thing, the entropy of the cold thing goes up a lot. The entropy of the hot thing goes down, but not by as much. So when you add them together, the total change for the universe is positive. It's spontaneous. The other way around, the numbers just don't work. The entropy of the universe would decrease, and nature just says nope.
So here's the bottom line. It all comes down to the sign of that total entropy change. If it's positive, the process happens. It's spontaneous. If it's negative, it absolutely will not happen on its own. In fact, the reverse process will. And if it's zero, the system's at a perfect standstill. It's at equilibrium.
Okay, but to measure all these changes and compare them, we need a starting line, right? A common reference point, an absolute zero. And that is exactly what the third law of thermodynamics provides.
The third law is actually really elegant. It says that at the coldest temperature that's even possible, absolute zero, a perfectly ordered, pure crystal has an entropy of exactly zero. Why? Well, think about it. If it's perfectly ordered, there's only one single way to arrange all its atoms. There is no disorder, so its entropy has to be zero.
And that, right there, is huge. It gives us a true, fundamental baseline. It's like putting a definitive stake in the ground that says, this is zero. Every other entropy value we ever calculate is measured from this one starting point.
And the real payoff of having this absolute zero is that we can now measure and create tables of entropy values for all sorts of substances under normal everyday conditions. These are called standard entropies, or S0, and they are one of the most important tools a chemist has.
All right, enough with the theory. Let's actually put these laws to the test. Let's combine the second and third laws and see if we can predict whether stuff will happen in the real world.
Okay, classic example, an ice cube melting. We know that the process of going from a solid to a liquid makes the water molecules, our system, more disordered. We can even measure that change. It's an increase of 22.1 joules per Kelvin. But is that enough? Does that mean it will always be spontaneous? Let's find out.
Now this is where it gets really cool. The answer completely depends on the surroundings. At -10 Celsius, it's cold. For the ice to melt, it has to pull heat from those cold surroundings, which causes a big drop in the surroundings' entropy. So big, in fact, that the total change ends up being negative, not spontaneous. But at +10 Celsius, the surroundings are warmer. Pulling that same amount of heat out doesn't cause as big of a drop in their entropy. So now the total change is positive, and boom, the ice melts. The math perfectly explains what we see every day.
And what's amazing is that this same exact logic works for chemical reactions too. Thanks to those standard entropy values we can look up, which exist because of the third law, we can predict the entropy change for pretty much any reaction. We just add up the entropy of all the products and subtract the entropy of all the reactants.
So let's try one. How about the combustion of methanol? You know, you start with some liquid methanol and oxygen gas, you burn it, and you get carbon dioxide gas and liquid water.
First step, we just grab our tools. We go to the data tables and look up the standard entropy for each of the 4 things in our reaction.
Then we just plug the numbers into our formula, and wait a minute, the result is a negative number. The entropy of the system actually decreases. So how on earth can this reaction be spontaneous? Well, remember, that's only half the story. This is a combustion reaction. It releases a ton of heat into the surroundings. And that massive release of heat causes a huge increase in the entropy of the surroundings, way bigger than the decrease in the system. So the total change for the universe is positive, and that's what drives it forward.
Okay, so we have been deep in the details, right? Definitions, math, examples. But let's pull all the way back. What's the big takeaway here? Why do these 2 laws matter so much?
To put it simply, these laws are pretty much the operating manual for the entire universe. The second law is often called time's arrow because it defines the one-way direction that all things naturally move in towards more total entropy. And the third law gives us that rock-solid foundation we need to actually calculate it all. Together, they explain why the universe works the way it does.
And hey, don't just take my word for it. The famous astrophysicist Arthur Eddington said this about the second law over a century ago. He knew it held this supreme, unshakable position among all the laws of nature.
And this all leaves us with one last, truly mind-bending question to chew on. If the total disorder of the universe must always go up, constantly moving towards a state of maximum possible entropy, what does that mean for the ultimate fate of all the stars, all the galaxies, all of us? Something to think about.